Yes, thank you. I am going to present a idea which is in part new, and a couple of technical results, in particular one specific technical result in classical GR that supports it, but which is based on the work of a lot of people who actually are here. The specific things I'm going to present are done by this group of people here. Francesco is here, Haggard is my main collaborator on the classical metric that I will present, and these are the people who have worked out most the phenomenology. So this is a preview of the main message that I'm going to give you. So it's 3 points in order of increasing of decreasing certainty. The first one is that a black hole can quantum tunnel into a white hole without affecting the external metric, the far external metric, which is something that if you're a relativist and you think for a moment, you would say, no, that's impossible. And I hope I'm trying to convince you that that's not impossible and tell you why and where it comes the wrong intuition about that. The second is that given that this process exists in nature, in principle, I believe so, how long does it take? If it takes much longer than the Hawking radiation, it's not a very physically relevant process. I want to argue that there are reasons to believe that perhaps it takes less than the Hawking evaporation, and I'll tell you what are these indications and what are the actual calculations that one can do to check that. And the third is that if it is true that this process is shorter than the Hawking evaporation, and if it is true that there are primordial black holes, we would like to claim that this phenomenon may lead to possible observations. And in fact, that one possibility is that it has even already been observed and is connected to these mysterious things, which are the fast radio bursts that the radio astronomers have been puzzling around a lot in the last years. So that's the overall story. I'll spend some time to explain what is this phenomenon I'm talking about, and then I'll go to the next one. So we're talking about black holes. The situation of black holes, of course, is that we have the classical picture, which is wonderful, very credible by itself. Then with the Hawking radiation picture that improves on it by taking into account what happens to quantum field theory over the classical geometry. But we know that this is not the end of the story. We all know that this is not the end of the story, and that's one reason we're here somehow, because that's not the end of the story. And there are two questions. One, which is most awfully posed, which is what the final state of the black hole, and related to that, what happens to information. There's a way I would rephrase the question in a way that sounds more interesting, at least to myself, which is what happened at the center, what happened at the singularity there. What do we miss in these two pictures? Of course, we miss quantum gravity. That's not been folded in, and the reason is that we don't have yet a strongly enough theory or tentative theory of quantum gravity to actually compute what happened at r equals 0. But the point is that quantum gravity is not necessarily quantum field theory on a given metric, that's on a given geometry. There's more into quantum gravity than just fields on a given geometry, because there is more into quantum fields than just perturbation theory because of a number of reasons, because you can have superposition of geometries. Quantum gravity is a quantum theory of geometry. I think that there is a step to be made, which a number of people have been made recently in a number of manners, to try to understand black hole not just in terms of quantum field theory on a given geometry, but in terms of the quantum theory of geometry itself. The point has appeared various times during the discussion here. So, as I said, one way I would like to phrase the question is what happened at the quantum region. Clearly, general relativity is not telling us that there is a singularity, right? In the physical world. General relativity is telling us that there is new physics there. So it's wrong to say that we have a credible prediction there is a singularity. It's right to say that there's a credible prediction that approaching high curvature regimes, quantum mechanics comes in, and therefore we don't know what happens. So what happens at r equals 0? All matter goes there, right? Everything that falls into a black hole goes there. I'm not asking how the information goes out, as it remains on the horizon, it remains outside, there's a way the Hawking radiation comes out. I'm asking very simply and directly what happens to the actual thing falling in. Okay, fall into a black hole, we see things falling into a black hole, we see them, or sort of. We see the accretion disks, and we see that in finite proper time, we believe that in finite proper time they go in. We believe the picture across the horizon, a very big chunk of space-time across the horizon, until near r equals 0. What happened there? Well, it might be that it simply disappears. Space-time ends, period. There's nothing to say anymore there. It might be that it sort of emerges in another universe in some strange way. It may be that it stays there together forever, like what we used to think by being just classical relativists. You know, the black hole's there, and from the point of view of the outside, it stays there forever at least. Or it may say that it comes out. And it seems to me that of all these hypotheses, the last one is by far the less courageous and the less speculative, and the most what a classical normal conservative physicist like me would like to look at first. And the idea is very old. I'm now just rapidly reviewing the old story of this idea. I've been able, or my collaborators, have been able to trace it back to the late 70s. In fact, Frolov and Vygotsky, this is a paper. This is a picture from their presentation, I mean, long ago. You see, there is something collapsing and then bouncing out, emerging, and this is a horizon which is not an event horizon because it doesn't go out to scry. Is just an isolated horizon or a trapping horizon or dynamical horizon, whatever. And there is an internal horizon. We have heard about this possibility from Bardina yesterday, I think. The two meet later at some times because the internal horizon is going to grow and this is going to shrink. And so there's only a trapped region here, but the global causal structure of space-time is just trivial. And the physics is exactly the one we know until sometimes, but then what happened is somehow less dramatic than what we expect with the eternally existing horizon or information disappearing sometimes. Information that go in clearly can go out here without any problem. So this was just not much more than a picture. Steve Giddings came out with the idea of remnants, which is sort of similar. The horizon ends, and then there is some internal thing that can last longer, can last short. Several people who are here actually developed this at the end of the beginning of the 90s by trying to make it more precisely now by writing a metric explicitly. And what they did is to, and this is very relevant for what will come out in a moment, try to glue the metric of a collapsing star with a black hole to the metric of a white hole, okay? By just cutting at some time and cutting at some time and gluing, and at least at that time, they would cut before the actual formation of the horizon. This is obviously a precursor of Herard's recent ideas that somehow what comes in, you get the information directly out in a sense without needing to go inside the black hole. In this millennium, Aschecker and Bojewald try to, again, without writing explicitly a metric, to propose what they said what we call a paradigm, in which there is a region of space-time, this gray region here, which is quantum, okay? Meaning, we can give a classical, a good classical description of whatever happens outside here, but there is a region where classical theory doesn't work, and we can either describe it with an effective metric, a metric that doesn't solve the classical equations, or if you want to be more precisely, not use a metric at all, like when you have a particle that tunnels through a wall, you don't have really a trajectory. The way you can think about is that the wave packet, which is sort of spread and doesn't follow classical trajectory, and then you can, on the other side, measure it and go back to a classical picture. Again, there was no precise metric which we could write here, and then the list goes on. In more recent time, there are several people. Bodin is one of them. Sabine has some work in this. It's a long list of people. This is Hayward in 06. He wrote explicitly a metric. This is its causal structure, in which, again, there is an outer horizon, an inner horizon, and a phase in which the star collapses, a phase in which there is Hawking radiation, but then again, everything is, information comes out and everything is, all this was either done without a specific metric or with a metric which is just guessed without solving the Einstein equations. And all this was thought, apart from Abai and Ashtekar and Bourgeois paper, thinking about a metric with quantum mechanics over it. What about quantum gravity itself? Well, there was a crucial paper, at least for our work, a completely crucial paper. That was our starting point by Klaus, who is here, and Peter Hadicek, in which they did something very remarkable, in my opinion. They actually computed a quantum transition between a black hole and a white hole in an extremely simplified model. What they did is the following. They took generativity with spherical symmetry. They took a null shell, so moving radially, null just because it's simpler, and they wrote the equation of motion of that. And of course, you have one single degree of freedom, which is where is this shell, essentially. And you write the classical equation, you write the phase space. The phase space is very simple, it's two-dimensional, essentially. And it's disconnected in two parts. The two parts are the one where the shell comes in and the one where the shell comes out. And for each one, you can write the full metric around. And this one, you have the shell falling into its event horizon here and then getting to singularities, a black hole, and this one is coming out. But this is a simple system. It's one-dimensional plus whatever constraint. So you can do the quantum theory exactly, and that's what Hadicek was very good and Klaus is good in doing. So they wrote exactly the quantum theory. They wrote the Wheeler-DeWitt equation, and they studied the evolution of wave packets. And the magic is that a wave packet that starts here can continue there. So the two disconnected components of the phase space are not anymore disconnected. So the Wheeler-DeWitt equation connect them, in a sense, and you can have an evolution from one to the other. So you can have a black hole forming, so some matter that collapses from a black holes, and then a quantum mechanical evolution that comes out there. Now this is beautiful and attracting, and so there's some very attractive aspect and some difficulties to be addressed. The intriguing aspect is that, why not? Why couldn't something coming in, quantum mechanical bounce out through a tunneling process? After all, we know that classical forbidding evolution is possible quantum mechanics. So it may be a question how long, but why not? In particular, this may take time, in some appropriate meaning of time, which I'll go to make a transition from black hole to white hole. But remember that Hawking radiation takes forever, right? If you have a stellar black hole, its evaporation time, I don't remember the number, but it's something like 10 to the 50 the age of the 10 to the 50 times the age of the universe.
10 to the 60 something.
Thank you. So even worse. So 10 to the 60 times the age of the universe. So we are talking about the process of Hawking evolution that don't think of it as something that is going to happen tomorrow, right? It's something enormously more large than any time scale we've looked. So it's not absurd to ask whether there is anything happening at a shorter time scale. Now, the problem is that with this approach, as far as I could say, Klaus is in and maybe is jumping on me, but there's no way to estimate this transition time. So I'm here at some radius. I see the thing coming out. After how long do I see the thing? I see the thing coming in. After how long I see the thing coming out? So what could determine the tunneling time? And then also, here I have two asymptotic regions, this one and this one. In a sense, I would like to identify them. Is there a way of having something like that in the real universe? And that's our question. So there is a theme here, a common theme. Maybe things can collapse and come out. Maybe something happened inside r equals 0, which is very simply a bounce. Okay, things come in, bounce out. Now, bounce is not so absurd because, after all, let me skip this for a moment. That's what happened in loop quantum cosmology. This is the Friedmann equation. This is in red is the correction, and what happens? This is rho is the energy density. Rho Planck is density of the Planck density essentially, and what happens is that when rho becomes near rho Planck, this goes to 0. So it's like an effective pressure. The universe collapses, becomes very small. There's a pressure, and it bounces back, which, if you think physically, that's what quantum mechanics is all about, right? If you have a hydrogen atom, a classical electron falls radially into the nucleus, quantum mechanically it just stops because there is a Heisenberg principle, so it cannot go too small in the sense that it bounces out. Or if it is non-elastic, it stays there. So couldn't we think physically that there is some pressure there? And notice that this is important. This doesn't need to happen at the Planck length scale. Because physically what we expect to be relevant is the curvature to be Planckian, namely the density to be Planckian. Now imagine you have a star, okay, the sun. And so the star is here, 10 to the 13 centimeters. So imagine it collapses, or so something a little bit bigger than the star that collapses. It forms a black hole at a kilometer or so, okay? And then, according to the current picture, the star, it falls in. It becomes smaller, 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 smaller. Now, here is a Planck length, the 10 to the minus 33 in length dimension. The Planck density is reached here, 10 to the minus 12, which is enormous compared to the Planck density. So we are talking at the phase of a collapsing star, we call it a Planck star, when it reaches the Planck density, which is still enormously bigger than a few Planck lengths. The Planck density is the density that you obtain just with GH bar and the question is what it is numerically? It's a Planck mass over a Planck volume. It's a density that you obtain if you squeeze a Planck mass into a Planck volume. Depending if you put G equal 1 or H equal 1, or it's 1 in G equal H equal C equal 1 units. Sorry? Yeah. Yeah. So it's a high density, but it's still over, in this case, sort of 10 order of magnitudes. It happens when the star is 10 order of magnitude larger than a few Planck length. So when something collapses, we don't get to the quantum gravity regime at our more or less a Planck scale, but much, much before that. So that's Planck scale. So that's when the bounce is reasonable at this length here, where this is the mass of the star. Now, suppose I take this extremely vague picture that I've given you. So it's a black hole forms, the thing bounces, comes out, and it comes out of a white hole. Now, every relativist here, and there are remarkable relatives here, would say this is impossible because you cannot go inside a black hole and come out a white hole because, of course, you can put a black hole. This is the internal black hole. This is the internal of the white hole. Of course, you can put it in the same metric, but they're the wrong way, right? In the Kruskal extension, the white hole comes first and the black hole comes after. So there is no metric here which is a vacuum solution of the Einstein equation. It has to be a vacuum solution of the Einstein equation. So what else happened here? It's nothing. That I cannot fill this region here with a vacuum solution of Einstein equation. So this is an incoming shell. Here I can put flat. Here I can put flat because inside the shell is flat. This is a quantum region I don't care, but what about here? Okay. Well, this is the classical GR technical result I'm giving you, which somehow makes the scenario plausible. This is the Kruskal extension. You have the incoming shell, okay? you don't care about the inside is flat, and consider this piece of Kruskal. So you have at the outside the black hole and outside the incoming shell, including the interior of the black hole. Okay? Put it on a side and consider the outgoing one and do the same thing. Okay? Consider both. Take the dark gray matrix and the light gray matrix, just write them in this way, oops, and fill in between the quantum part. What you get is this. So in other words, take a space-time with this global structure, which is flat here, flat here. Here is Schwarzschild, but is locally isomorphic to Schwarzschild, but not globally isomorphic to Schwarzschild, because the map from here to Schwarzschild is not one-to-one. A point here and a point here, they overlap into the extended Schwarzschild. Once you understand it, you just write it down. It's just a little exercise to write it down, to write the various, put the coordinates and do the gluing and do all the thing, and that's the result, but essentially I've given you the full metric. So this is a metric. The metric is well-defined all over outside. And I just describe it a little bit better. You start from Minkowski. You have an incoming shell. It enters into its own black hole. Here is Schwarzschild. Here is inside the black hole. Okay? And then the statement is that you can continue this metric. Here is still Schwarzschild. Here is a white hole. And here is the outcoming one. And here is the flat space again. The fact that this metric exists, which was not obvious, and there's a small technical classical GR result that allows this picture to become credible, shows that if quantum physics here is possible, if quantum physics allows this metric here to tunnel to this metric here, then you can have something incoming, quantum tunneling to a white hole and outgoing, without affecting anything here, with only one asymptotic region. So you can have a local phenomenon confined in space and in time, which is a transition from a black hole to a white hole. So I see no reason for this not to happen. Now, if you write this metric explicitly, I gave you the full equations. You see it depends on essentially two constants, or more precisely 4 constants, but 2 just determine what happens inside, so when you enter the quantum region here and how far you go here, and then 2 constants that affect the metric outside. And the 2, one is the mass. You have a shell, so it has a mass, so different masses give a different metric. And then there's delta. Delta is the radius of this point here. So it's how far from the horizon when you map it into Kruskal, the incoming, outcoming shell overlap. Okay, so what's the radius there? It's 2m plus delta. Now, what does it mean, this delta, from the point of view of the outside? Well, this is the fun part of the story. Remember that in GR, clocks go at different times, of course. And when you go in the mountain, you become more old, and when you stay near the sea, you remain more young, because time goes faster there and shorter there. So this phenomenon is more of Earth, but is huge in a black hole. So on the metric, I have the metric everything. Here, I have preferred the frame, which is the one of the shell, of the star. So in that frame, I can compute the time from one point to another point, inside and outside the shell. Okay? So I'm inside the shell. I see from some shell being in some position, shell comes in and goes out, and I have a proper time, tau internal. And I'm at some fixed radius r here, and I compute the proper time here. Now, I'll tell you in a minute how do these numbers come in, but if I put reasonable parameter here, say a mass, which is the mass of a star, I can get this as a millisecond, and this is the age of the universe. So this phenomenon is a phenomenon with a huge time dilation, obviously, okay, from the inside to the outside, which explains the bounce idea. So the star collapses, bounces, and bounces out. If I look from the outside, I see this bounce, but in slow motion. So what's a black hole from this picture? A black hole is a rapidly collapsing and bouncing star that, because of the generativistic time dilation, I see it in an enormous slow motion. The slow motion can last for billions of years. So if you enter into the shell here, you just in a millisecond jump out there a billion a year later. A black hole is a shortcut to the future. Is the picture. Boom, and outside, there's a huge amount of time. So delta, I didn't show it. Delta is exactly what determines this long time here. So if you take the metric and you compute this time here, there's a part that depends on the radius, of course, how far they are, time it takes light to go in, come out, and then a part which depends logarithmically on delta. Delta is very small, so this is a very small negative number, so this is a very small positive number. So very small delta is a very long time here. So what determines delta? And, or in other words, how long does this phenomenon take? A priori, there are many things you can imagine. You can say, oh, well, it's tunneling, so it has to be something like exponential in 1 over the Planck constant. So dimensionally, 1 over e to the m squared is infinitely long. Or you can say, well, this should be something of the order of the Hawking radiation or shorter, and m log m is a result of the first wrong calculation that we did, which is definitely wrong because it's too short. Now, I'm not going to discuss, because I don't have time, all these various options, but I have a number of indications that that's the most credible duration of this. But let me, before telling you the indication, let me tell you how, in principle, you can compute it. You need a theory of quantum gravity. So this is how you would compute it in loop quantum gravity. Okay? In loop quantum gravity is sort of designed for computing these kind of things.
For tunneling, we expect a tunneling factor exponential of something. So what is it here in your previous slides? Is it the mass of the shell or what?
Yeah, the mass of the shell over the Planck mass square, the exponential of that.
So this is what, well,
you
m
need
squared divided by what?
m squared divided mass Planck square,
Oh,
and then you have a Planck mass in front of it dimensionally.
So this is the tunnel factor.
That's, yeah, that is the, yeah. But that's, it's going to be corrected by a phase space factor, which could dump it. I'm not going to go.
But not exponentially. I mean, that is the.
For a black hole, it's exponential because it's counted by the number of states, which is the entropy, which is, again, exactly e to the minus m squared. So that's why we don't believe this is a credible, just first guess. I'm not going through this. These are the basic equations of loop quantum gravity. I just want to say that in loop quantum gravity, you have states associated to a boundary of a four-dimensional space-time region, and you have transition amplitude given by some integrals. So the way it works is that if you have if you know the geometry on the boundary, then you can compute an amplitude associated to this geometry of the boundary, right? Inside, there is no metric. You're sort of summing over all the metric, right? You're summing over all the metric intuitively, bounded by this region and integrating over them with exponential of the action. So the previous equation are a concrete version of that calculation. So again, these are the states are in some Hilbert space, well defined there, have the interpretation of geometries, and these are the transition amplitudes. So the way you would do is take this surface, which is this one in Kruskal, take this surface, which is this one in Kruskal, and write a geometry here, and compute the transition amplitude between the two. Okay? And in the loop theory, you can do it order by order in some expansion, and you get an amplitude. And this amplitude depends on what? Depend on the geometry here and the geometry here. But the geometry here depends on the mass, on the two parameters that the initial geometry that I gave you, so m and delta. So you get an amplitude which is a function of the mass and delta, which in the quantum theory become the spin associated, the mass is the spin associated to the spin network here, and delta is related to the extrinsic curvature, is related to the SU2 group element associated with that. These are technicalities, not important. The amplitude becomes a relation between the mass and delta, and you want to know when this process is possible, so when this amplitude, the modulus square of this amplitude becomes of order 1, so you get a relation between m and t. And this relation of m and t is what you want, the time as a function of the mass. Let's try to guess it. Instead of doing this calculation, which we are heavily and painfully trying to do, solving these integrals on SL2C and so on, let's try to guess what we should expect. In the geometry, the quantum region must leak out from the horizon, obviously, because if it doesn't, the horizon goes to Scri plus, and it is a event horizon. So you want some quantum effect to be outside the horizon. This is why this is not captured, some quantum gravitation effect to be outside the horizon. This is why this is not captured by quantum field theory on curved spacetime. Okay? Now, the usual argument against this possibility of this effect is that outside a big hole, the curvature is small. So if the curvature is small, you don't expect quantum gravity effect to be large, because quantum gravity effect happen at curvature of the order Planck scale. But there's a missing parameter in this argument, because the time should fold in. Tunneling is something which happens even when you think you're very far away from a quantum regime, but you wait for a long time. If you use this argument for an uranium atom, it never decays. But the uranium atom does decay. Why? Because what matters is not just how far you're away from a quantum regime, but how far you're away from a quantum regime and for how long. So if you fold in the time, you can write a parameter, Q, a dimensionless parameter, which is the curvature times the time you wait, times the Planck length, which is when this equal to 1, you enter into a quantum regime. And now you can compute it on the metric, and you find out that there is a certain radius at which this becomes order 1 first, and that it takes a time m square to become of order 1. So this is the argument, the indirect argument that we use to suggest that perhaps t is m squared. Now, the Hawking time is m cubed, so that's much shorter. Still very long. For a stellar black hole is more than the age of the universe, but it's not 10 to the 60 time the age of the universe. So let's take this seriously as a hypothesis and see what it implies. For a stellar black hole, this time is still longer than the age of the universe, so we're not seeing anything. For a galactic black hole, even worse. What about small black holes? Now, suppose it's true that there are primordial black holes. Okay? There's a cosmology, a long-going discussion on the possibility of having small black hole of all possible masses formed in the early universe. Now, a small black hole forms here and bounces and explodes immediately, but of course immediately from the inside. Outside, it's a long time. Since I know T is m squared, the relation between time and mass, here I know the time, this is the time, our time. So I know the mass. If I know the mass, I know the size of this object. So I have the prediction of an object of a certain size, which explodes, which have a certain number of signals coming out of it. First guess, so thing explode, and we can observe it. First guess, very naive, so basic physicist would say, well, this is a certain size. The signal that come out will have a component with a wavelength, which is the size of the thing. You compute it using that, and you come out So this is a Schwarzschild radius of something exploding today. This is its energy, so it's something of the size of the moon, roughly. Sorry, the mass of the moon and of the order of a millimeter, or less than a millimeter. This is a Schwarzschild radius of the moon. And this is not far away from the 20 centimeters wavelength of the fast radio burst. So it's a wild guess, but it's a possibility. The astronomers, you will hear more from Francesca about that. The astronomers have seen these signals, which are very mysterious. They are in the radio. They were observed by the Parkers in Australia, and then confirmed by Arecibo in the Caribbean. There is this very, very strong burst in the radio with this wavelength. Here is a guess. They are primordial black holes tunneling and coming out. You'll hear more from Francesca about that.
They would be arriving now. They would be tunneling within the Hubble time.
Yeah, so exactly. So we think that there are three kinds of black holes, right? The ones primordially created, and the stellar ones and the galactic one. The stellar one and galactic one are out of the game from observation.
So,
if they're primordial black holes, I know the time they lived because they lived the age of the universe. And if I know the time they lived, I can know the mass of the ones that they were.
So what is the typical starting mass of one of these?
Moon. The moon.
Moon.
Yeah. So less than a planet. A bit less than a planet. There's also a high energy component, but Francesca will tell about that. And the beautiful part is that this is true. There will be we can be checked for sure if we see enough of these objects, because there will be a relation between the distance of the object emitting the signal and the wavelength with a characteristic shape. Again, you will hear more from Francesca about why and how, but there will be a smoking gun checking whether the hypothesis is right or wrong. So let me summarize. That's basically what I want to say. So there is a technical result, is a solution of classical GR, is an exact solution of vacuum equations, plus incoming Null shell and plus Minkowski, which describe something that collapses, a small region where the equations are violated, of course, because it's a quantum region, but which is compact in space and time, and then things coming out. This shows that this process of bouncing a black hole to a white hole is physically possible. And the question is how long it lasts. In principle, at least with loop quantum gravity, you can compute this time. We are trying to do this computation and sort of struggling with it. I expect that other approaches to quantum gravity could do this computation, so maybe they should be done. And what this computation should answer is how long does it take? Does it take a time proportional to the mass square, mass cube, mass? If, as we suspect, because we have indirect argument, the time is less than the Hawking time, then, first of all, the information paradox disappears because things come in and then bounce out. There's no event horizon, in a sense. And more interesting, the actual explosion of this, in principle, is observable for sufficiently small, sufficiently old black holes, so typically for primordial black holes. And we even have a guess of an observed phenomenon which could be related to, could be that. Of course, this is a long shot, but this thing is interesting. Thank you.